Good evening, everyone. I'm Calvin Joseph, and today I'm going to conduct the problem solving and doubt clearing session for the course Control and Tuning Methods in Switch Mode Power Converters for the week. Okay. So today the outline or the various topics which we will discuss are as follows. One is we will discuss about the steady state parameters, like is the current ripple, voltage ripple for buck and boost converters. Primarily today I'll be focusing on the boost converter. Then I'll also be talking about the fixed frequency modulation techniques. What are the control techniques are there? Then also sir had taught variable frequency modulation technique. When the frequency changes, the switching frequency changes. Next, we will consider the DCM operation, that is discontinuous conduction mode operation, followed by certain questions and MATLAB demonstrations. So, are there any doubts, queries, or any topics you want me to focus on? Or whether you want me to directly start solving sums, already you can let me know. Okay, if you're not able to hear me or if something is not clear, you can stop me and ask me. All right, you can unmute and you can ask the question, or you can send a message on the chat as well. Okay. So there are various steady state parameters which sir has taught. One is the inductor current ripple, that is the ripple in the inductor current. Another is the output voltage ripple, that is the output voltage capacitor ripple. So let me write. It's better if I write. Today we are discussing week 2. Okay. One is the inductor current ripple. So that is usually in this form, like this, like this, like this, like this. Okay, this is your inductor current ripple. This is your IL average value. Okay. This is your time period T. This is your on time, T on. This is your off time. Okay. This is your rising slope, M1. This is your falling slope, M2. So in our analysis, what do we consider the inductor current is triangular waveform. Okay, it is linearly rising and it is linearly falling. It linearly rises and it linearly falls. That is the assumption which we have, and it is roughly valid and it is used all over. Okay, so this for the inductor current ripple. So this is your inductor current ripple. Okay, this is your inductor current ripple, and this will be delta IL current ripple by 2. This will be delta IL by 2. Okay, so this is your half of the current ripple, etc. Okay, so this is true for your buck converter, for your boost converter, and etc. Okay, only your M1, M2 will change, your time will change, your voltage gain expression will change. But this is how the inductor current waveform looks like, and this is how the current ripple is there for the inductor current. Okay. So any doubts till this part? Okay, one more thing is what sir had told. Okay. Like actually, so this is your time, this is your inductor current, this is your zero inductor current. Okay, this is your graph. So now, this is my valley point, this is my peak point. Okay, as you would have heard when you have gone through the lectures, you would have heard about something known as peak current mode control, valley current mode control, hysteresis current mode control. All that you would have heard. So these are with respect to the peak and valley, how they control those aspects. Okay. So I have made many questions for those control techniques, etc., so that you will be able to understand those techniques better. So from the question, I'll be trying to float a concept which you will be able to understand so that you can visualize it, etc. Okay. So this is the inductor current ripple. And is ripple good or bad? Okay. These are actually switched mode power converters. That is they are switching. It is either on, off, switches on, switches off. When switches on, current is rising. When switches off, current is falling. So this is how it works. Okay. So there will be current will rise, current will fall. Okay. And this ripple also is there. It is present and it is also required. If your ripple is too less, that means your inductance is very high. Your converter will work slowly. Okay. It cannot respond fast. So we want the converter to respond fast. So we set the inductance value a little bit lower and the ripple will be more. Okay. So there are various trade-offs, etc. there and all. One more aspect sir told is the RMS. Your RMS value sir had told. So what sir had shown is there's a formula. That is, this is your time t. This is your time t, right? This is your waveform I val, I peak, and again it is coming here. So this is your entire periodic waveform. So your RMS, so your IL RMS square, that will be equal to, as per Sir's formula, it is 1 by T and x1 square plus x1 x2 plus x2 square upon 3, where x1 is your IVAL, x2 is your IP, right? Okay. Into your T1, that is this time T1, and this your time T2, plus again from here to here. So this is your x2, this is your x1. So it is plus x2 square plus x1 x2 plus x1 square by 3 into T2, the whole. Therefore, your IL RMS square is 1 by T into x1 square plus x1 x2 plus x2 square into T1, sorry, T1 plus T2 upon 3. Okay. This is for this case, this type of inductor current. This is when it is operating in continuous conduction mode. When it goes into discontinuous conduction mode, the formula will change slightly. We will look into that as well. Okay. So now T1 plus T2 is equal to T. Therefore, your IL RMS square actually is what? X1 square plus X1 X2 plus X2 square upon 3. Okay. Then you can substitute. What is your X1? It is I valley. Your X2 is I peak, right? So your IL RMS square is I valley square plus I valley into I peak plus I peak square upon 3. Okay, any doubts till this point? Okay. Okay. So now, okay. So now, what is your I valley? Your I valley, let us go over here. Your I valley is actually your IL average minus delta IL by 2. And your I peak is IL average plus delta IL by 2. Okay. This your I peak is IL average plus delta IL by 2. I valley is IL average minus delta IL by 2. Okay. So I will write I value is IL average minus delta IL by 2. I peak is equal to IL average plus delta IL by 2. Okay, so that I will substitute over here. What I will get? I will get my IL RMS square is equal to, okay, let me take this, okay, let it be. So this is 1 by 3 into IL average minus delta IL by 2 square plus IL average minus delta IL by 2 into IL average plus delta IL by 2, okay, plus I peak square is IL average plus delta IL by 2, the whole square. Okay, so what does this become? IL RMS square is 1 by 3 into IL average square minus IL average into delta IL plus delta IL square by 4. Okay, because this is A minus B the whole square. Similarly, this is A minus B into A plus B. That is actually A square minus B square. It is simple. Okay, so this will be what? IL average square minus delta square IL by 4. Okay, plus this is A plus B the whole square. So you have your IL average square plus IL average into delta IL plus delta IL square by 4. Okay, so if you notice, right, this and this get cancelled. This and this get cancelled. So what we are left with, sorry, IL RMS square is equal to 1 by 3 into 3 into IL average square plus delta IL square by 4. So that actually is equal to IL average square plus delta IL square by 12. Okay. So this is the same formula which sir derived. So I've derived it in a different manner, in a different way. Okay. Similarly, you have output capacitor voltage also will have some ripple everything. You can derive that as well. Now, we'll consider what are modulation techniques. Okay, there's something known as pulse width modulation, trailing edge, leading edge, and what is the latch. All this was done over here. Okay, so we'll see fixed frequency, modulation technique. Okay, so how do we, what we have is we have some gate signal like this. Then your inductor can rise like this, fall like this, rise like this, fall like this. Again, gate signal comes, again it will rise. So this is your inductor current, this is your gate signal Q. This is valid for a buck converter as well as for a boost converter. Now your Q is the gate signal for your main switch, main control switch. Now, how do we generate this Q? If this time T is fixed, then it is known as fixed frequency modulation. Okay, we can fix the time period, that is good. Now we want to fix the width. This is the width of this pulse. When we are trying to change, when we are trying to adjust that width, that is known as pulse width modulation. That is known as PWM. That is pulse, this pulse, the width of that pulse, you can either increase it or like you can make it like this, You can increase it or reduce it. That is known as your pulse width modulation. Okay, PWM. Now, how do we generate that? How do we change it? Okay, so for that, what is done is we have what is known as, we will have one signal. Okay, this is the time period. We will have one signal going like this. Okay, this is our signal. This is our ramp signal going from 0 to, let us say, V max. 0 to V max. Okay. Then at this point, this is my V control signal. So when my V control is greater than my RAM, what will happen? Then my signal, this is not good. When my V control, that is the green thing, is more than my blue RAM, then my signal will be high. Okay. And then once my RAM becomes higher than my control signal, it will go low. Again, when my RAM goes to 0, my Vcon is greater than my RAM, again it will go high. Then once my RAM goes higher than my Vcon, again my signal goes low. So this is your gate signal Q. Okay, so this is how it is generated. This is how it is generated. Right? So if we want to set the duty, let us say 50% or 40%, our Vcon should be X times Vmax, where X lies between 0 to 1. So if you want your duty to be 40%, that is 0.4, then your Vcon should be equal to 0.4 into V max. Okay, it should be 0.4 into V max. So this is how the duty is set in this way for your converters, for running it in open loop. So any questions till this point? Okay, all of you are very quiet. Okay, good, good. Okay, so this is our duty we have got, all that we have got. Next, there is a case known as current mode control. Like this is based on PWM. Next is we generate these gate pulses using current mode control. Current mode control. Okay, so in current mode control, what happens is we have a sorry. Let us say this is my reference. This is my peak reference current which I'm setting. And this is my inductor current. This is how it looks like. Okay. So this is my 0T, 2T, etc. What happens at 0? Your inductor current is low. Your switch is turned on. Once your switch is turned on, your current starts rising, it is increasing. Then it will reach this peak limit which is set. And when it touches this peak limit, that time it goes low. That time your gate signal will go low. And it will continue. And then when your gate signal goes low, what happens? Your inductor current will start falling. It will fall, 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 fall. Once it reaches T, again this gate signal will go high. It goes high, and it will be high, 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 high until the current reaches the peak. And then once it reaches the peak, it will fall. It will fall. And then this current also will fall, and it will proceed further like this. So this is the gate signal Q which is generated. So in the previous case, if you remember, what you did was you actually had some ramp. This ramp you had, and you're comparing some control voltage with the ramp and generating this gate signal. It's going high and low, high and low. In this case, in current mode control, you're using the actual inductor current. As we said, we consider the inductor current is triangular. It may not always be perfectly triangular, but it more or less appears as triangular. You can see. So we assume the inductor current is triangular, and then when it reaches the peak and then falls down, this is how it looks. So the comparison which we were previously doing using some own ramp which we generated, now actually using the buck or boost converter or whichever DC-DC converters, actual inductor current, we are using that for comparison, and that is generating a gate signal. So that is known as current mode control. Okay. This is a bit of an advanced thing. We will look into some sums, etc., and it will become more and more clearer. Okay. I'm just floating the concept, floating the idea. Then when we get into sums, we will understand it in terms of the sums, in terms of those numbers. Okay. So this is for current mode control, fixed frequency. Then we can have what is known as variable frequency. Variable frequency current mode control. What we currently have is this time is fixed. This is fixed. But what could change is if this T off was fixed. If this T off was fixed, then what will happen? This T on will be adjusted. This T on will be adjusted, and then the control would happen. That is another type of current mode control, where we keep our T off fixed, and the T on gets adjusted based on comparison with the ramp, with the reference value. Okay, that is known as a constant off time control. Constant off time control. Okay. You can also have what is known as hysteresis current mode control. That is, you have a peak, you have a valley, and your current, when it touches the valley, what will happen? Your gate signal will go high. When it touches the peak, your gate signal will go low, and then your current falls. Then once it touches the valley, again your gate signal will go high. Then it will reach the peak. Again your gate signal will go low. This is how your gate signal looks like. So what we are essentially doing is we are controlling the ripple. The current ripple delta L is fixed using this hysteresis current mode control. All right. It is fixed. But this time period T can change. This time period T can change depending on the input voltage, depending on the output voltage, etc. It can change. And this is the way, and hysteresis current mode control is supposed to be very fast. It has a very fast response, but there are certain challenges while implementing it. Okay. So this is done. Okay, we'll see discontinuous conduction mode. So till now, in all the diagrams which I was drawing, what I was drawing was this my inductor current going high, low, and this is my gate signal. Gate signal is like this, like this, like this, etc. So, and this is the zero value of my current. This is my IL and this is the zero value of my current. So my current is not going negative. It is not going negative. It is always above zero. Okay. And this is my Q. There can be a case when it can go negative. That is, your current goes negative. This could be a case. And that time the gate signal is like this. This time it is high, low, high, low, high, and low. This is the gate signal. This is the inductor current. Huh? So your inductor current is going negative, and it is possible because you are using a synchronous buck or synchronous boost converter. It is possible. When does this happen is when we have, let us say, a boost converter. This is your V in, this is your L, this is your Q, this is your Q bar, this is your capacitor, this is your load. Okay, so this is your IL. So in some cases, when your Q bar is on, your current, this current actually is becoming negative. It is flowing like this. So current is flowing like this. This happens in this case, in this time, when your current actually is negative. But this happens because we are considering that this is a switch. Suppose we replace it by a diode. L, this is your Q. This is replaced by a diode, which is the normal conventional boost converter. Then what will happen? Your current cannot go negative. So what would happen in that case is your current would start, it might go to this value, it might fall like this, and then it will remain zero. It will remain zero. Then it will again rise, it will again fall, and it will again remain zero. So this is known as DCM operation. When your diode comes into the picture, and because of the diode, your current is not able to go negative. And this is known as continuous conduction mode. When even though your current is very low, your current is able to go negative. Okay? This happens when we are using this mode. And DCM happens when we are using this mode of operation. Hmm. So, any doubts still here? Okay. So let us go to some sums. Okay, what have they given here? They have given input voltage is 12 volt, your output voltage is 48 volt, your switching frequency is 200 kilohertz, your output power is 100 watt. Okay. They are asking for the expression for current ripple, output voltage ripple, for how much is the inductance required, what is the capacitance required, what is the critical resistance RC, and what is the RMS inductor current at rated load current. Okay. Let's tackle it one by one. Hmm. So this is question 1. This is for a boost converter. B in is 12 volt, V ref or V output is 48 volt. Output power is 100 watt. And your switching frequency is 100 kilohertz. This is the given in the question. What do we have to find? We have to find what is the expression for delta IL, what is the expression for the output voltage ripple, what is the inductance required, what is the capacitance required, what is the critical load resistance, and what is the IL RMS. Okay, these are the 6 things which are required. Okay, so can you tell me how should I proceed? Like, what should be the first step that I do? What should I consider? What should I do?
We can find duty ratio.
Okay, duty ratio. Okay. Duty ratio is 1 minus V in upon V output. So that will be how much?
0.75.
Okay. So that is actually 1 minus 12 upon 48. So that is 0.75. Okay, then next what I should do?
L into delta IL by T on is V in.
Yes, yes, correct. So let me explain the boost converter. If we do over here. So this is my input voltage and my inductor is given here. This is my IL. The advantage of many places why do they use a boost converter is because they want the input current to be continuous. That is one of the reasons boost converter is used for like power factor correction, circuits and all. Okay, because you want your input current to be continuous. Okay, so this is one point I like to tell. Next is there are 2 modes of operation. If we are considering CCM, one mode is like this is your path, this is your output capacitor, it is discharging into your load, right? This is your case when Q is equal to 1. This is the case when Q is equal to 1. This is your V output. In your next case, that is you have your V in, you have your L. This part is connected, this part is open. This is your capacitor, and this is your load resistance, R load. In this case, Q is equal to 0. Okay, so there are 2 modes. Now, in this mode, your current will rise. Here, your current will fall. Okay. What about the output voltage? What will happen in this Q equal to 1 case? What will happen to the output voltage? Will it fall or rise?
It will fall.
It will fall because your capacitor is discharging. Your capacitor is discharging through the load. In this case also your capacitor is discharging, but your current is being fed. This is your inductor current is also being fed into your circuit. Okay, so when Q is equal to 1, what will happen? Your current will rise and your output capacitor will discharge. It will discharge through the load. When Q equal to 0, your current will fall and your output capacitor will discharge through the load, but your inductor current will also charge it. Okay, so that's why your output capacitor voltage will increase. So what happens in a DC-DC power electronic converter is, for some time your inductor current will rise, sometime your inductor current will fall. For some time your output voltage will fall or it will rise, and for other time it will fall or rise. Okay, they will work like that. It will not be like the voltage will just keep on increasing or the current will keep on increasing. That's not the way it works. That's not how it is supposed to function. Okay, so this is for the converter, this is for the boost converter. So if you will see, let us say, let us say this is your IL, this is your IL, this is your Q, okay? This is your Q. What will happen to your output voltage is a little bit tricky to understand. When your signal is Q is 1, what happens? Your output voltage is discharging through the load. And when Q turns 0, it will charge. It will charge. Again, it will discharge. Again, it will charge. That is how the output voltage will charge and discharge. Now, how do we understand whether the output voltage is charging or discharging? That we have to draw what is known as the capacitor current. That is this current. Okay. In this case, what is your capacitor current? Your IC is equal to minus I naught. This is your capacitor current in this configuration. In Q equal to 1. But when Q equal to 0, your IC is equal to IL minus I0. Okay. Your IC is equal to IL minus I0. So, when Q equal to 1, your IC, it's actually not a straight line. Suppose this is 0. When Q equal to 1, your IC will actually be minus I naught. This will be minus I naught. And then when Q equal to 0, it will go like this and it will go like this. It will follow how your inductor current looks. If this is your inductor current, like that only it will look. So this will be the inductor current minus the output current. Then when Q again goes 1, it will again become minus I naught. And then when Q goes low, it will again follow the inductor current minus output current. So this is the waveform of IC. So when your IC is greater than 0, that time your output voltage will increase. When your IC is less than 0, then your output voltage will reduce. Any questions in this? Okay. I think it will be better if I show a simulation. It would be easier for you guys. Let me show that. One more. Okay, I'll run a simulation and then we'll be better for you to understand. Okay, this is my inductor current, this is my output voltage, and this is my gate signal Q. So let me stop it. So I'm stopping it. Let me zoom in steady state. Okay, let us see 3-4 cycles. Okay, let us see this. So my Q is high. Okay, my Q is high. Q is high like this. My inductor current is rising. It is rising. When Q becomes 0, my inductor current starts falling. So for inductor current, it is a bit easy for you to understand, visualize. When Q is 1, it rises. When Q is 0, it will fall. But for the output voltage, what will happen is when Q is 1, the output voltage is falling. It is falling. And when Q is 0, the output voltage is increasing. Okay, so this is the waveform for the output voltage. Now, what is actually causing that output voltage to fall or increase? That is dependent on the current through that capacitor. Okay, so now let us look at the waveform of the current through the capacitor. So, here, this opening. Okay, so this is the inductor current. You can see the inductor current is going from, let us say, from 4.5 ampere to almost 14 ampere. So this is the current ripple. This is known as the current ripple. Okay. If you see the I out is the output load current. That is very low. It is of a very low ripple is there. Okay, it is having a waveform close to the output voltage because it is just a scaled down version of the output voltage. V out by R. Okay. The thing of interest is the IC current. IC current. So when my Q is 1, that is my inductor current is rising, my capacitor current is actually my output current, minus output current. So it is like around minus 2.5 something, minus 2.3. And then when my Q is 0, when my inductor current is falling, my capacitor current goes to the inductor current value minus my output current. So it looks like this. So this peak, which is 12, is actually my inductor current peak minus the average of the output current. So it is at this value. It is my IL minus the I output at this value. So that's why I output is 2.3. And here this is like around, say, 13.8 minus 2.3. That comes out to be 11.5. So this is around like 11.5 ampere. So this is how it will look like. Okay. So when my capacitor current IC is greater than 0, in this region it is greater than 0, then my output voltage will increase. In this region it is less than 0, my output voltage will fall. Any questions in this? Okay. Okay, so let's go for the sum. So what they have told is you have to find the expression for current ripple. So this is my rising slope and this is my falling slope for my current. So in this case, you see what is the voltage applied across the inductor? It is V in. The voltage across the inductor is V in. So your rising slope is actually V in by L. Okay, this is the slope at which the current is rising for the inductor. In this case, what is the voltage across the inductor? The voltage across the inductor is V in minus V out. Since my output is greater than my input, the voltage across the inductor which is applied is actually negative, right? So that's why my slope M2 is actually V out minus V in by L. So this is my slope M2. Any queries till this? Okay. So what we know is this is my current ripple. So my current ripple is given by V in upon L into dt. V in upon L is what? M1 into my T on. This is actually M1 into T on. Okay, that is V in upon L into dt. So what is our V in? Can anyone tell what is V in?
12 volt.
12 volt. L is not given actually. Okay, D we found out to be 0.75 and T is 10 microsecond. Okay, so the delta IL will be equal to 12 into 0.75 into 10. What is that? Hmm.
90.
Sorry?
90 into 10 raised to minus 3.
Okay, 19 to 25 minutes. Right? What about others? Did others also get the same value?
10 raised to minus 3.
10 raised to minus 3. So it is 10 to the power minus 6, right?
Okay, sorry. 10,
Hmm.
10 raised to minus 6.
Yeah. So this will be 19 to 10 raised to minus 6. Okay, so this is my delta IL, right? So this expression we have got. Now for the output voltage ripple, this is what I was saying is, when my switch is on for T on time, my current to the capacitor is minus I output. So my delta V output is equal to my I output into the on time by C. So this is the expression for the output voltage ripple. So this is actually equal to I output into dt upon C. D and T we know, we don't know what is I output. How do we find out I output? What is given to us?
100 watts by 48 volt.
Yes. Output power is given 100 watt. Okay. So output power is what? Output voltage into my output current. So my output current is actually P out by V out. That is 100 by 48. 100 by 48 ampere. So my delta V naught is equal to 100 by 48 into the duty, that is 0.75 into 10 into 10 to the power minus 6 upon C. So how much is this?
15.625 into 10 power minus 6.
Okay. So it is 15.625 into 10 to the power minus 6 upon C. Okay, we got the A part is done, the B part is done. Very good. Now let's go to the C part. The C part, they're saying is what is the inductance required for 20% ripple current at rated load current. You want 20% current ripple at the rated load current. So what is our rated load current? Our rated load current I naught is 100 upon 48. What is that?
2.0833.
So that is 2.0833 ampere. What is my IL average for the boost converter?
I0 by 1 minus D.
Yes. IL average is actually I0 by 1 minus D. That is 2.0833 upon 1 minus 0.75. So that is how much?
8.33.
Okay, so that is 8.33 ampere. This is the value of IL average. Now, we want my delta IL to be 20% of this IL average. Okay, so what is that value? %20 of IL
1.67.
is 0.2 into 8.33, which is actually, as you said, 1.667 ampere. So this is my delta IL. Also, we have already found delta IL is what? 19 to 10 to the power minus 6 by L. So 90 into 10 to the power minus 6 by L. So our L is 90 into 10 to the power minus 6 upon 1.667. So how much is the L?
$53.98 microhenry.
Yeah, so it's around approximately 58 into 10 to the power minus 6 Henry. So L is approximately 58 microhenry. Okay. Any doubts in this part? Okay, no doubts. Now the D part is, what is the capacitance required for 1% output voltage ripple? Okay.
Sir, one doubt.
Yes.
Normally, current ripple will be expressed as percentage of output current, right? But here we have taken 20% of IL.
Yeah. Because normally when you see, they would have written it for the buck converter. In the buck converter, your IL average is same as your I output load current. But in case of the boost converter, it is not the same. That's why we have to change.
Okay.
Because your ripple current is dependent on your input and output voltages. That is one part. But you want it to be you design it in such a way that it is like 20% or 30% or 40% of your rated load current. Rated load current, not rated load current, of your rated inductor average current. Okay. Based on that. Because if you would have designed for 20% of your load current is already 2.0833 ampere. And on top of it, you make it 20% of 2.0833 ampere, it would be like around what we'll say, like around 0.4 ampere or something. That ripple current is very, very small as compared to your average current, which is not acceptable. That's why we do it for some factor of your rated average current. In the
Okay,
case
sir,
of
understood.
So now we want delta V output be 1% of your output voltage, right? It is 1 by 100 into 48. So I'd like to stress the fact that 1%, whenever percent is there, you have to scale it by 1 by 100. Okay, that is a standard which you must remember and follow. Okay, so your delta V output is coming out to be 0.48 volt. This is the permissible ripple. But we already found an expression for delta V output, that is 15.625 into 10 to the power minus 6 upon C, right? So 15.625 into 10 to the power minus 6 upon C is equal to 0.48. So this implies, what is your value of C?
$32.55 microfarad.
15.625. 15.625 into 0.48. Sorry, 15.625 divided by 0.48. Okay, 32.55. Sorry, I had made a mistake. So it is 32.55 into 10 to the power minus 6 farad. So it is 32.55 microfarad. Okay. So any questions still here? Any doubts? Okay, I know we are going very slow. There are many questions, so I better hurry up. Next part is, what is the critical resistance RC for DCM operation to start? Okay. So what happens in this boost converter, when your load resistance R load, when it will increase, when your R load will increase, what will happen? Your I naught will reduce. When your I naught will reduce, your IL average also will reduce. And there could come a situation where it could operate in this DCM mode of operation. Okay, but before going to DCM, there is a mode known as CRM. In CRM, what happens is, your current will start at 0 and it will fall back again at 0. Again start at 0 and fall back at 0. So this happens at a resistance which is your critical resistance, critical load resistance RC. So we are supposed to find this value of RC. In that case, what is happening is, this is your IL average. This is your delta IL. This is your delta IL by 2. Yeah. So your IL average is equal to delta IL by 2. Okay. Suppose your R becomes greater than RC. Then what will happen? Your IL average will be less than delta IL by 2. That means the current will become like this. This is how the current will be. We will draw straight. This is how the current would be ideally in CCM or in CCM mode of operation. But if your diode is enabled, that is, you are not allowing it to current to go negative, then this will not be valid. This cannot happen. In that case, what will happen is your current will go to some value, peak will be more, fall, and remain at 0. Go to some value, fall, and remain at 0. Okay, this is how it will look in DC. Now we have to find this IL average should be less than delta IL by 2. This should be the condition. So your delta IL, you have found out, right? Your delta IL is given by this. delta IL is 2.667 ampere. Right? This is fixed. So 1.667 ampere. Okay, you might ask that this is for your rated load condition. This is for your rated load condition, but this ripple remains the same because ripple is dependent on your input and output voltage. It is not dependent on your actual load current. Right? We just take it as a factor of it, but in actual practical reality, your current ripple is dependent on your input and output voltage because your current ripple is determined from your inductor volt second balance. It is not like capacitor charge balance. So, what is your IL average? It is Vref upon your R load, that is your I out, into 1 upon V in, right? And your delta IL is V in upon L into dt. Okay. So, IL average is less than delta IL by 2. So, your Vref, okay, it's Vref square. Vref square by R load into 1 upon V in is less than V in upon L into 1 minus V in upon Vref. Sorry, Vref or V output is the same into your T. So, we have your V output square upon V in into 1 upon R load is less than V in upon L into V output minus V in upon V output into T. So you have V output cube, V input square into L upon V output minus V in into 1 upon T will be less than R load. So your critical resistance RC is V output cube into L into your switching frequency into your V in square into your V output minus V in. Okay. So can you find this value? Your V output is 48 cube. L is comes out to be, what is your L? L came out to be 58 microhenry. 58 into 10 to the power minus 6 into switching frequency is 100 into 10 to the power 3 divided by V in square, that is 12 square, into V output minus V in, that is 48 minus 12. So how much is this RC? Yeah, it is 123.73 ohm. Correct. Your RC is 123.73 ohm. Now let us go to the next part. They're saying what is the RMS current at rated load current? Okay. What is the RMS inductor current at rated load current? So we had found already, right? IL RMS is equal to square root of IL average square plus delta IL square by 12. IL average we found out to be 8.333 ampere square. Delta IL I think is 1.667 square by 12. So can you tell this value? Yes, it is 8.346 ampere. Okay. So any queries? So I agree this first question is a very lengthy question, took a lot of time. So I'll just give a recap. What we did was we found the expression for current ripple, which is Bn upon L into dt, because when considering the inductor current is rising. Next, we saw the expression for output voltage ripple. This is also found when during the on time. This minus I output into your dTA upon C. D we wrote it as in terms of E with input, output, etc. Then we are considering that rated load current is there. So rated load current approximately proportionally your rated average inductor current will be there. We're finding 20% ripple current for that value. Then we find the capacitance required for 1% output voltage ripple from the previous expression. Then we found the critical resistance RC for DCM operation to start. And then also we check the RMS inductor current. So many points, many things which sir has taught in the previous week has been touched upon in this one question. We have done ripple calculation, we have done DCM operation, we have done design of inductor, design of capacitor. All this has been done in this example. Okay, so I'd like you to, understand what has been done, why it has been done, etc. I know these concepts are quite advanced. It takes lots of time to understand it. That's why also simulations also are provided. But you should try to understand and do accordingly. These videos will also be uploaded. So I'll be uploading it to this channel. Let me put it here. So this is my YouTube channel where I'll be uploading this video. Okay. You can refer to this for anything. And also the notes which I am adding, I will post the link to those notes in my YouTube video as well. And I think you will get an Excel sheet from NPTEL team. There also you have the link to the video and the link to the channel as well. Link to the notes as well. So I'll proceed with the next question. Question 2 is PWM operation. So this is a simple question. And okay, RC once again. Okay. Yeah. This is the expression for RC. So you cannot remember this expression for RC. You'll have to derive it in the exam. Unless you are very smart, I will not be able to remember. So if you understand the way to derive, it is easier. Okay. Now we'll proceed to this question. This is pulse width modulation. We are considering a boost converter which is operating under PWM. We are considering the ramp's maximum voltage is 2 volt. And we need to find the control voltage. Okay. So in this question, question 2, your V ramp is equal to 2 volt. That it is going from here, 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 here. Okay. So this value is 2 volt. This value is 0 volt. This is your time, right? Your input voltage is 12 volt. Your output voltage is 30 volt. Boost converter. So how much is the duty which you require? Can you calculate and tell me? Okay, I'd like all our esteemed participants also, Ankita, Anusri, Naveen, Srisha. You guys also can answer. Don't feel shy. Okay, it can be right, it can be wrong. But be more interactive. Okay, thank you. So your duty is coming to be 0.6, which is correct, right? So your duty is coming to be 0.6. So you need to set this is your control voltage, right? This is your Vcon. Okay, my drawings are not very good, but this is your Vcon will be a fixed value. So your Vcon will be what? Your Vcon should be your D into your VRAM. This voltage you must set. So that will be 0.6 into your VRAM, that is 2. So what will be 0.6 into 2? Okay, 0.6 into 2 will be 1.2 volt. Next part of the question is saying that your switching frequency, let us say, is 100 kilohertz. If your switching frequency is 100 kilohertz, what will be your time t? Yes, thank you. If your switching frequency is 100 kilohertz, what will be your time t? Your time t will be 1 by 100k, that is 10 into 10 to the power minus 6, that is 10 microsecond. Okay? And this has a slope. This slope m is given by VRAM max value upon your time t, that is 2 upon 10. So this is in terms of volt per microsecond. So your slope is 0.2 volt per microsecond. Okay, this is known as your RAM rate. Okay, this is your RAM rate. So now I'll go to the next question, okay, which is peak current mode control. So now I'll be focusing a lot about current mode control, which will be showing in implementations and in various aspects in the future lectures. But I just have some certain sums, which I hope will introduce you to these concepts in a better way. Okay. So now we are going to question 3, which is related to peak current mode control. Okay. Again, I'm using the same thing. V in is 12 volt. Okay, this is like a kind of standard thing. I'm working on this as well as it is more easier for me. So bear with me. So V in is 12 volt, V output is 48 volts, switching frequency is 200 kilohertz, output power is 100 watt, inductance is 10 microhenry. Okay. We have V out 48 volt, switching frequency is 200 kilohertz, your output power is 100 watt, and your inductance is 10 microhenry. All right. What is your current ripple? Your current ripple is given by this expression Vn upon L into dt, right? So that is 12 upon 10 into 10 to the power minus 6. Your duty is 0.75 as we previously calculated for this gain. It is 0.75 into t in this case is 5 microsecond because your switching frequency is 200 kilohertz. So it is into 5 into 10 to the power minus 6. So what is this current ripple? Can you calculate and tell me? Okay, thank you, honestly. So the current ripple comes out to be 4.5 ampere. Okay, it is 4.5 ampere. So very good. You guys are going very fast. We found the current ripple. But we know what is the output current. Load current is 100 upon 48. That actually is given by 2.0833 ampere. Okay, 2.0833 ampere. Now they are saying in the question, it is asked, what is the control voltage required at the rated load? The rated load is rated load current is flowing. So as we previously calculated, our IL average is I naught upon 1 minus D. So that comes out to be 2.0833 upon 1 minus 0.75. We are already calculated, it is 8.333 ampere. This is fixed. This is a value. So now, what is my peak current? This is my inductor current, right? This is my IL average current, which we got. This is my delta IL. So my I peak is equal to IL average plus delta IL by 2. So that is 8.333 ampere plus delta IL is what? 2.0833 ampere by 2. So what is this value? Can calculate and tell me? Okay, very good. 9.375 ampere. So this is my peak current. So the control voltage, which I must set, should be at this value, right? This should be the value which I must set, right? And if we consider unity, sensing, gain, etc., this should be around like 9.375 volt. We'll have to set it as the control voltage. So this is my reference current. Okay, so this is for peak current mode control. Question 3. Now I'll go for the next question. Question 4. We are considering COT, constant on-time current mode control. Okay. Question 4. Constant on-time current mode control. In this case, what happens is this time T on is fixed. This time T off will adjust and will get adjusted depending on my input, output, load, all that. T off will get adjusted. But my on time is fixed. Okay. So what do we have? We know that delta IL is V in upon L into T on for the boost converter, right? What do we have? Input is 12, output is 48. We want a current ripple of 1 ampere. Current ripple has to be set as 1 ampere. So this should be 1. This is 12. What is the L given to be? 3.3 microhenry. So L is 3.3 into 10 to the power minus 6. So what is the expression for T on? T on is 3.3 into 10 to the power minus 6 by 12. So what is that value? Yes, 0.275. So this 0.275 into 10 to the power minus 6 second. So it is 0.275 microsecond. Okay, we found T on. But what is the T off in steady state? This is your M1. This is your minus M2. So what do we know is M1 into T on should be equal to M2 into T off. This has to be followed when it is in steady state. So your T off will be equal to M1 into T on by M2, right? So M1 is given by what? V in upon L. M2 is given by V output minus V in upon L into T off. So what happens? Your L and L get cancelled. So this becomes equal to T off is equal to V in upon V output minus V input into T on. Now your total time which it took is this time T is equal to T on plus T off. This is equal to T on plus V in upon V output minus V in into T on. So this is equal to V output minus V in plus V in upon V output minus V in into T on. So that is equal to V output into T on upon V output minus V in. So can you calculate and tell me what is this value? Our T is 48. T on is 0.275 into 10 to the power minus 6. 48 minus 12. What is the time? Okay, T off is 0.0. T is 0.367 microsecond, correct? T is 0.367 microsecond. So your switching frequency, that is equal to 1 upon T. That is what? That is 2.72 megahertz, correct. That is 2.72 into 10 to the power 6 hertz. So it is 2.72 megahertz. Okay. So any doubts still here? Okay, many people are there. Naveen, Shrisha, Ankita, Anusri, Prasad Rao. If you have any doubts, you can stop me and ask me. Okay, then we proceed to the next question. Next question we are considering hysteresis current mode control. Okay. Hysteresis current mode control. So parameters remain the same. The inductor current ripple is set to 4.5 ampere. What will be the resultant switching frequency? Okay. So we have this question 5, right? Question 5. Hysteresis current mode control. So what happens in hysteresis current mode control? We have a peak reference. We have a valley reference. And this is the current. It goes like this, rises, falls, rises, falls. Touches the peak, falls to the valley. Touches the peak, falls to the valley, like that. So this is my delta IL, which they told it should be 4.5 ampere. Okay. This is the rising slope M1. This is the falling slope minus M2. This is fixed. What we know, what do we know is delta IL is M1 into T on. T on is this small duration, right? Delta IL is M2 into T off. This also we know, right? So what had we found over here? T is equal to T on plus T off. Okay, let me write better. Mhm. Okay, better than that, T on is delta IL upon M1. T off is equal to delta IL upon M2. So your time period T is T on plus T off, which is equal to delta IL upon M1 plus delta IL upon M2. Your time period T is delta IL into M1 plus M2 upon M1 into M2. Okay, this is the expression. Now, switching frequency is 1 upon T, that is equal to M1 into M2 upon M1 plus M2 into 1 upon delta IL. Okay. Now, what is your M1? Is V in upon L. Your M2 is actually V output minus V in upon L. Right. Your M1 plus M2 is equal to V in plus V output minus V in again. So that is equal to V output by L. Right. That you have to substitute. So your switching frequency is equal to M1 is V in upon L. M1 plus M2. So M2 is V output minus V in upon L. M1 plus M2 is V output upon L into 1 upon delta IL. So 1 L gets cancelled. So your switching frequency expression is what? V in into V output minus V in upon V output into 1 upon L into 1 upon delta IL. So can you find the values? V input is 12, V output is 48. L is given to be 3.3 microhenry. So can you find the values? Okay, delta IL is 4.5 ampere. Your input is 12 volt, your output is 48 volt, your inductance is 3.3 microhenry. Delta IL is 4.5 ampere. Yeah. So it comes out to be 606.06. 606.06 kilohertz. Okay, you can do the calculations. Arun has been able to do it very fast. Okay. So now let's proceed to the next question. Constant off-time control. So what are statements are true of constant off-time control? So is the switching frequency fixed in constant off-time control? And is a minimum on-time required? And constant off-time is similar to valley current mode control or peak current mode control? In constant off-time control has a fast load step-up response, but a poor load step-down response. So which of the statements are true? Can you please let me know? Okay. What about Ankita? What about Srisha? What about Naveen? Just tell. Take a guess. What do you think is the right answer? Or what do you think are the right options? If you have any doubts, queries also you can ask. Okay, all of you are being very silent and shy. Okay. I don't know whether you all are understanding everything or they have taught too well or I not taught at all. Okay. So question 6. This is regarding constant of time control. So what happens in constant of time control is this time t on is adjustable, but this time t off is fixed. So if you will notice carefully, t is small t. T on is small t, so it is variable. T off, T is capital T, so it is fixed. That's why if you would have remembered for constant on time, I had put T on, capital T on. So this case, I'm using small t on because there in constant on time control, my T on was fixed. But now when we're doing constant off time control, my T off is fixed. That's why this is my capital T off. Okay, I hope till this part is clear. So this T on is variable. This T on is variable. But the T off is fixed. Now, when we're doing current mode control, we have one fixed reference here either. This touches this point, okay? And then it will fall, it will fall, it will fall, it will fall. For how much time? For this T off duration. Then again it will rise until it touches. And then it will again fall for this T off duration. So one thing I'd like to point out is that this point and this point need not be the same. In transient case, it will not be the same. In steady state, it will finally settle at the same value. Okay, but in transient, it will not be the same. So now my T off is remaining fixed, but my T on can get adjusted. So the T on is coming from the control loop. From the control loop. Whenever it touches my peak, then only it is switching off. So that is controlling my T on. So my T on is being actively controlled, but my T off is fixed in my implementation. So that is known as constant off time control. Okay. When you do constant off time control, one important thing you have to make sure is there should be some minimum T on should be there. Because in case of boost and buck boost converter, a minimum T on is required. If you don't give that minimum T on, there could be a case that the output voltage will rise or it will either collapse. That can also happen. Okay. So you need to have a minimum on time. This minimum on time should be there. Since my T on changes, my T off remains fixed. So that means my total time period is varying. So that is why it is a variable frequency operation. So it is variable frequency. Right? So let us go back. So the switching frequency is not fixed. So this A is false. Minimum on time is required. Yes, it is required. True. Constant off time control is analogous to valley current mode control. No. This analogous to peak current mode control because we are controlling the peak of the currents. Right? That is why it is analogous to peak current mode control. Constant off time control is a fast load step up response but poor load step down response. Okay, this I have to explain. So what is a load step? Load step means what? Your output current was suppose let us say this value. Then it goes up suddenly to this value. So this is the step up. This is the known as the step down. Okay, this is the output current. Now, what happens to the load current? What happens to the inductor current? Let us say inductor current is going like this, like this, like this, like this, right? When this, your output current can change instantaneously because your load may change, but can the inductor current change instantaneously? No. Inductor current cannot change instantaneously. Why? Because it is an energy storage element. We know that the inductor, it resists the sudden change in the inductor current. That is the virtue, the property of your inductor. So if your inductance is very high, then your current will change very slowly. That's why we prefer in these power electronic converters to reduce the value of inductance so that the current can change suddenly, fast. Okay. So let us see there's been a load step up. Load has been stepped up. So what can happen is the current, what we would like is the current should go like this and go like this. This is what we prefer. And when a step down happens, it should go like this and it should go like this. This is what we prefer. This is what is desired. But what happens? When we are operating in constant off time control, that means this off time is fixed. This off time is fixed. This off time is fixed. So this T on, it can be adjusted. So it can work like this. It is possible for it to go like this. So the step up, this is known as the step up part. So the step up performance is good. But when we go to the step down, I have drawn the desired values like this. But actually, what would happen is it would be like this. It would go like this. For the off time, which is there, small on time, minimum on time. Again, the off time, fixed off time. Then the minimum on time. Again, the fixed off time. Then the minimum on time. Again, the fixed off time. Then the minimum on time. Again, the fixed off time. Then the minimum on time. And so on. Then it will reach the steady state. So this is the step down. So the step down performance is poor, but the step up performance is good for the constant off time control. Okay, this is an advanced thing. This would be taught by sir in the coming weeks, lectures, everything. Okay, this I just wanted to put it in the question. Like I put it, I'm just floating these points so that when sir will teach you later, you will understand, you can recollect. Okay, and I'd like to say that this course is a very, very difficult course. It is not at all an easy course. You just go through the lecture once, doesn't guarantee that you will remember it, you will know it, you will understand it. It's no guarantee. What you could do is you could go through the lecture, you could make the notes, you could close the book, you try to recollect what sir told. You try to recollect what was the steps followed for derivation. What was the steps followed for finding the current ripple, for finding the output voltage ripple? What was the step followed for finding the inductance, the capacitance? How does the waveform look for peak current mode control? How do you set the control voltage? So you should be able to summarize it. Should you be able to summarize it to yourself? That's when you remember little. That's when you have understood little. Okay, so that you have to repeatedly do. And the advantage with this course is that you are going to do MATLAB simulations. So that will reinforce the concept. It will get into your head. So for that, you have to do the simulations. Secondly, these topics are linked. Okay, what you learned here, you would be using in the further lectures. So that's where it will get further and further strengthened. Further and further, you will understand. Okay, all these things you will not understand at the spot instantaneously. You will not understand. You will understand a small part. Later, you will understand another part. Later, you'll understand another part. Then finally, it will all make sense. Okay. So don't get discouraged. Okay. I know this is a very tough course. It's very hard for me also to teach, right? And since we are working on this, it is manageable for me to teach. Otherwise, it's very difficult, right? So I know it will be very, very hard for you guys to understand, very, very hard for you guys to learn, right? But be patient and try. Hmm. Okay. So I'll go to the next question. which is the discontinuous conduction mode DCM. I think we have already done DCM. DCM we had already done. We had to just find the critical resistance. There was a formula also which we wrote. And then what happens is that critical resistance you could get. Next, we have to find the duty required when your R is 2 RC, when your resistance is twice the critical resistance. When your resistance is twice the critical resistance, what happens is it will operate in pure DCM. Okay, let me just show this part. Let me just show it to you. Let me simulate this in MATLAB. This is like a sudden relief you will get. Sorry. So let's simulate this in MATLAB. Okay. So sir has been demonstrating MATLAB extensively. I'll also suggest that you guys do the MATLAB simulations. It's very useful, very practical. You would use in your projects, you would use in your research, you will use it. And it's required. The concepts will really get strengthened when you do it. Okay. Sir has used this approach of parameterization to run it from a script file. Because I remember when I was doing my internship and I didn't know MATLAB very well. So I used to go into my Simulink file. I used to go and what will I do? I will set this value D into 100. I'll calculate to be 75. Then I will do some changes. Then I'll understand, oh, my D into this should be 60. Then everywhere where my D into 100 should be there, everywhere I must go, I must change that value. And this is a simple simulation. That time I was running for some motor current signature analysis something. So everywhere I'll have to go and change the value and do. So that was a big headache. Okay, then later on I realized there's a way to, to parameterize. It becomes easier. You say that this is the value I want, and everywhere where D is used anywhere inside your simulation, it will take that value and it will run. Anywhere where T is required in your simulation, it will take that value and it will run. That will make it very easy. Okay, that's very much easy. Similarly, there's these go-to blocks. Now this inductor current, I need it to be over here, as well as over here, as well as over here. Instead of drawing that wire, it will look very, very dirty, very, very hard. This makes it more easier to understand. Okay, this makes it more easy to understand. Okay. Next is, I'll go to my script file. I have considered two cases. One is my resistance is 20 ohm. This is my input voltage. This is my output voltage. This is my resistance of my switch, of my diode drop, inductance, capacitor ESR, switching frequency. Time period is 1 upon switching frequency. Now, as we derive, this is the formula for the critical resistance. Okay? And this is the output current. Now, in DCM, the duty will be different. In CCM, the duty will be different. Okay, let us see how. Okay. Let me run this. Let me run it for R equal to 20 ohm. We will run it. It is running. Let us see the waveform. This is a MATLAB plots. So this is my inductor current, output voltage. Okay. Gate signal. So you can see it is around 48 volt. There is some drop because of the parasitic resistances, etc. But it is around 46, 48 volt approximately. This is my inductor current. Its waveform is given here like this, right? So these are the waveforms and you can check it. But what is my duty? My duty is around 75%. Because we had calculated duty should be 0.75. So duty is around 75%. This is well and good. Now what I will do is my resistance. What is my critical resistance? Let us see what is the value of critical resistance. R underscore crit. That comes out to be 42 ohm. What I will do is my resistance, I will set it to be twice of that. So I'll set it to be 84 ohm. Okay. I have set my resistance to be 84 ohm. My duty will remain 0.75 ohm as it is. Will remain as it is. Now what I will do is I will run my simulation again and let us see what happens. See what is happening to the output voltage? It is keeping on rising. It is constantly rising. We know that for duty 0.75, it should be set like 48 volt, but it is going more than that. So why do you think that is happening? Any idea? Any suggestions? Why do you think the duty is going so, the output voltage is going so high? If you will see, my duty is still 75% only. But my output is going around 64 volt. So what should be done? You can see it is going to DCM. The current is getting clamped at 0. It is rising from 0, going back to 0. Again, it is repeating. So it is, for some period, it is settled at 0 ampere. So it is DCM operation. So what happens in DCM is the duty required, lesser duty is required. So to operate that way, there is a formula which I derived. For DCM, this is the duty which is required. The duty is dependent on the output current, on the switching frequency, etc. Okay. So what I will do is I will set my resistance to be 500 ohm, or let us make it resistance 100 ohm, which is more than my critical resistance, so it should operate in DCM. And then let me run the simulation. It's running. Now in this case, you'll observe it is staying around 47.5. So it is close to 48 volt. So it is not suddenly rising. It is not increasing drastically. Okay, and why this has happened? Let us check. What has happened is the duty has become less than 50%. Earlier we know for boost converter from 12 to 48 volt, it should be duty should be 0.75. But that equation is valid only for continuous conduction mode. When we go to discontinuous conduction mode, the duty which we found is actually in that expression, it is 0.4899, less than 50%. Okay, this is the duty which is required. Okay, and that is found by from this expression, which I had actually derived. Okay, this expression is used. Okay, so any questions?
Sir, one doubt.
Tell.
In that expression for critical resistance, is there a 2 in the denominator? But
No, this is V in square, V in raised to 2.
no, and the 2 into L.
Yes, 2 into L, yes. So Vref cube into 2L into FSW by Vn square into Vref minus Vn. Okay, let me check what we had derived, whether we had made a mistake. Okay, the resistance. Okay, we had forgotten delta IL by 2. Okay, let me correct it. Thank you for pointing it out. So this is delta IL by 2. So there's a factor of 2 ohms over here. Okay, 2. So, sorry, by 2 is over here, by 2. So that will be into 2. Okay? Yeah. So this I had messed up. I forgot. Hmm. So into 2 will also come over here. So this will be also into 2. So this will be around 124 into 2. So this will be 2 are approximately 248 ohm. Okay. Yeah. Thank you for pointing out. Okay. Any other questions or doubts?
Sir, one more query.
Ask
If
us.
if when we are modeling the switch, sir has added switch resistance R1
Yes,
in the
R1.
simulation.
Yes. Hmm.
Suppose we have to consider soft switching, then is it possible to consider that back and that diode across the switch and capacitance across the switch in this type of simulation, or we have to use that switch block in the simulation?
Uh, Actually, it's difficult to consider all that because those are very high frequency effects, everything, which have not been considered. Like sir, also in his model, sir has not considered, diode reverse recovery. All those things are not considered. We are just considering some, static characteristics of the parasitics, which play some role, some impact in steady state and in a transient operation. Now, all this, your reverse recovery, this switch capacitor charging, discharging, and soft switching, or that where the switch node, where the voltage rings to zero and then you turn on ZBS. All these things are difficult, very difficult to do in this way. It's not impossible, but it is difficult. It will be time consuming. Your MATLAB simulation also will run for a lot of time, etc. So it's not recommended to use MATLAB for those things. For those things, you could use MATLAB for that, but you could also use, simulation softwares which are made for power electronics, like, Plex you have LT Spice you have Simplest you have. Those would be good for those cases.
Because when we are reading papers,
Mhm.
the converters may be operating in many modes, mode 5 modes, 6 modes like that.
Yeah, like N mode.
So is it applicable in that? That is what I was thinking. Can we use this approach to simulate such converters?
Mm, yeah, like one student had done. They had done actually, but it takes a lot of time. Like you could use the actual switches in MATLAB. Let us say instead of going through this approach you can do. It's also good. Like this approach is more of a mathematical model based approach where you have this. Let us say very slow actually. MATLAB is slow today. Like you have this 1 upon s. You write them the equations, linear differential equations, which are switched everything, and you write. But you can also make the boost converter using the actual normal switch of a which is used. Like you could use a MOSFET. MOSFET. Usually I use this one. So this is the MOSFET. Drain, source, gate, etc. And here you can add the on resistance, diode forward voltage drop. Right. And if you want to add a parallel capacitance, you can just add a small capacitor in parallel to your drain source. That way also you can, that approach also you can use.
Okay, sir. Okay.
So this would be a faster approach, like using these MOSFETs, which are already available. You can add some parameters and you can run it. Because which converter are you working on?
No, I have not started working. I was just going through the literature
Okay.
of DC-DC converters.
Okay, you're targeting isolated ones, right?
No, non-isolated DC-DC.
Okay. On isolated
So
DC-DC, but
uh,
targeting the soft switching ones.
to incorporate soft switching.
Okay. Yeah. Actually, I haven't worked that much in soft switching, so I don't have that much of an idea. But yeah, soft switching would require variable frequency operation. Yeah. Because I had done on critical conduction mode. So there, because it goes into critical conduction mode, I use that constant on time control. And it for the current will go to 0 and then I will turn on. So that is like ZCS kind of way we are trying to mimic. So that one usually it ends up in variable frequency operation. Yes. Then any other queries?
No, sir. Okay.
So what about Ankita? No queries, no doubts. You understood everything, I assume. Okay. Okay, then any other like things like because the topic is quite advanced, right? And I'm solving certain sums. Like, what do you feel like? Should I solve more sums or should I show more MATLAB simulations? Or should I spend more time explaining theory? Like, what do you suggest? Since these
More
are
problems
no problems, okay?
and that true false questions, that was also good because we should understand some theory from those questions.
Yeah. Yes, that's why I decided like I had even one more question. Everything, these are all, but there's no time actually. That's right. Okay.
Okay, sir. Thank you.
So thank you then. Thank you for joining. I'll post the video soon. Good night. Bye.